Alrighty, this is 9-7, part 2. So we're going to do the Roman numeral 2. We're going to jump down and finish up our last couple of pieces here. So we're going to talk a little bit more about probability. So mutually exclusive versus inclusive. So exclusive, if something's exclusive, things are separate, right? If you're in an exclusive club, you're kind of separate from everyone else. What that means is there's no overlap in your sample space. Either you're this or you're that. There's no way that you could be double counted. It's just those two values. So if we look at what's exclusive, we would just find the probability of each one separately. There's no overlap, and we can just add them together. So this is the or situation. So when we're talking about this or that, if you look at the symbolism, I'm hoping that you remember that means intersection. So we're looking at what would be, or pardon me, union. So that would be what would be either in the first set or the second set. So U for union. So this would be like the union symbol. So when you think of it, it's like the or. So you're either in the first one or you're in the second one. So if they say these are mutually events that are happening in the same sample space, we have to be careful on whether we double count. So that's kind of, I guess, the whole idea of this part. So if they're mutually exclusive, I think it's easier to start with that. So we're going to do that one first. That means there's no overlap. So they're only in one set or you're in the other. So if we're doing an or here and we're talking about a union, we're just going to calculate. So probability of A union B. So this is an or. We just find the probability that A happens plus the probability that B happens. And you've been doing this all along. So like if you want to roll a 7 or you want to roll a 10, you'd add those two together and then you get the total number of ways. Or if you want to get a yellow marble or a blue marble, you'd add all the yellows together with all the blues. So if there's no overlap, mutually exclusive, it's pretty easy to do that. But if it's mutually inclusive, so that's what they're talking about here, the probability of A union B, so the or, well, it's either the probability of A plus the probability of B, right? So we still have those, but we have to subtract off the overcounting, the ones that are in both A and B. So it's the probability of A intersect B, the ones that are in both. So think of this like the overlap. There's a great question on our practice MCA that had a question just like that. So when we're calculating that, when it's inclusive, inclusive means that you're double counting. So I was going to talk about it's a great question on the MCA practice that had, what's the probability of choosing whatever the spade, whatever it was in a card, or a queen? Well, if you do a spade or a queen and you count up all the cards that are spades, 13, all the queens, 4, you've counted that one card that's both a queen and a spade twice, and you have to subtract it off. So it's really important to understand if your sample space has overlap in it when you calculate. But otherwise, just whenever you're saying or, we're adding together or totaling up those probabilities. All right, so let's try a couple. So it says here, back to our marbles in a box again, same exact ones. What's the probability that you choose either a red or a black? So the probability of a red or a black. All right, well, in your mind, you probably just total them up automatically, but technically, the probability of getting a red would be 3 out of 10. The probability of getting a black would be 5 out of 10. So together, we have an 8 out of 10 chance that that's going to happen. So this is the probability of getting a red plus the probability of getting a black. Now, do I need to worry about overlap here? Is there anything that's both a red and a black together? Well, no, the marble's either red or it's black. There's no like swirl of red and black or something. So we don't have to worry about this. These are exclusive, mutually exclusive. And remember, we can always reduce. So we can write that as 4/5. We could write it as 0.8, or we could write that as 80%. So that's really what we're looking for. Is it exclusive or inclusive? All right, let's try another one. You draw one card at random from a standard deck of 52. What's the probability that the card is either an ace or a spade? So the probability it's an ace or a spade. All right, so this is kind of like the example I was giving before. So how many cards in the deck are aces? Well, there are 4 of them. So this would be the probability of getting an ace. We'll think about that. Plus the probability of getting a spade, right? So if this was mutually exclusive, I would just do that calculation. So there's 4 out of the deck of 52 that are aces. There are 13 out of the deck out of 52 that are spades. I'd be done. But there are cards in the deck that's both an ace and a spade. There's one of them. So the ace of spades we need to, oops, not add, we need to subtract off, because what we've done is we've double counted that one. So we need to make sure we subtract off. I don't know why I can't write a subtraction sign here. We need to make sure we subtract off the ace of spades, because that one has gotten double counted. It was counted in our aces and in the spades. So we just need to be careful if there's things that are overlapping. So this would be mutually inclusive. There's something in common in both of those that we have to subtract off. So when we get our total here, we would have 16 out of 52, which reduces down to 4/13. And again, you can write that as a decimal or as a percent as well. So if we're looking for overlap, we just got to be careful we don't double count. All right, let's try a couple more here. So here's a chart that's showing how long people have worked at their business. So it's all these employees. And it says, what's the probability that an employee chosen at random has 30 or more years of its experience? So it's the or more part that makes this one of those probabilities where we're going to have to add, because there's more than one way to be successful. So 30 or more, I'm going to kind of draw a line here. So anybody in these intervals are going to be what we would call an event success here. So 35, 21, 8, and 2, all of those together will be success for us. So we need to total up the 35, the 21, the 8, and the 2 gives us 66 people. That would be what we would consider success. So notice we're adding though, right? This is probability of 30 to 34 plus the next category, the next category. So the probability that's 30 or more would be all of those added up. 66 out of, now we're going to need the total number of outcomes. In other words, the total number of employees. So we need the total for all of them so we can make that comparison. So that's 529. So that's about, I think the easiest way to do this is a decimal. It's about 12.5%. Now, when you think about this, why is there overlap or not? I mean, I didn't subtract anything off. Well, you can't be in more categories than one, because either you've worked there for 30 to 34 or you're up in the 35 to 39. Like, you can't be in both of those categories at the same time. You're in one or the other. So it's mutually exclusive, right? We don't have any overlap happening. So it's just always that conversation, do I need to subtract anything off? All right, let's talk about our last little parts here. We're going to talk about independent events and then complements. So independent means whatever you do does not impact what you do next. So they are independent. Like if you're independent, you stand alone, you do not, what you're doing doesn't affect what other people are doing. So if A and B are independent events, that the probability that both of them occur is the probability of A times the probability of B. And, right? Whenever you say and, we're multiplying. So it's really important when we're saying or, that's add. This or this, we're totaling it up. And means I want this and that to happen. That's a multiplication. That's a product. So if you want to find the probability of two independent events, you just multiply those probabilities together. So it's a pretty straightforward. We've already kind of been doing that. You do that kind of naturally. It's the shortcut for making the list. So we don't have to list out all the different ways we can do those outcomes. We multiply, and that's the counting principle, and it works the same for probability. All right, so let's talk about the difference between independent versus dependent. So we're back to our same box of marbles. It says if two marbles are randomly selected with replacement, what is the probability that both are yellow? Okay, so the with replacement means independent. Whatever I choose first does not affect what I choose second. So that means I have the same number of marbles when I'm selecting. I don't have to worry about having a less number or something like that. So the probability that they are both yellow, I have equal shot of getting a yellow on each draw because I independent. I put it back in there so I can draw it again. So I have 2 yellows out of 10 on the first draw, and I'm going to have 2 yellows out of 10 on the second draw. So it's a probability of getting a yellow on the first draw times a probability of getting a yellow on the second draw. So I have the same likelihood in each one of those draws. So that would be 4 out of 100 or 1/25. And again, you can write that as a decimal or a percent. How would it be different if I say without replacement? Well, without replacement means that I didn't put it back in. We would call that dependent. That means what I draw first is going to be affecting what I have left to draw next. So if I don't put the marble back in the bag, I have fewer to choose from. So when I talk about that probability, it's going to be a little bit different. So the probability of both yellow means I'm really doing the probability of getting a yellow on the first one, and then the probability of the next yellow followed by a yellow. But I don't have as many left in there to choose from. So on my first draw, I'm good. I got 2 out of 10. But on the second draw, what's left? Well, if I drew a yellow already, there's only 1 yellow left. And also, if I drew that marble and I kept it out, there's only 9 total marbles left in the bag. So when we're thinking about that calculation, it does affect the outcome, right? So what I'm doing does have an effect on what happens next. So that would be 2 out of 90, 1 out of 45. It's going to be a little bit different probability or likelihood. Let's try another one, so we can see what that independent versus dependent. All right, so we're going to talk about sales. So we have a salesman, and if on any particular day the salesperson has a 1/3 chance of getting a sale. So that's about what his sales record is. So out of 1 out of every 3 calls, he's going to make a sale. So say on one given day, he contacts 5 potential clients. What is the probability that a sale will be made on all 5 of his calls? Well, this is kind of like flipping a coin, right? If there's 3 outcomes. So it's a 1 out of 3. So on every single phone call, he's got a 1 out of 3 chance to make a sale. Now, if he calls this first person, the first call, he's got a 1 out of 3 chance because that's his sales record. That's what we're assuming. Once he makes that call, it has no impact on the next call. I mean, if he makes a sale or not, it's going to be the same one way or the other. So it would be a 1 out of 3 on the next one. And it's going to be a 1 out of 3 on the next one. So all 5 of those calls is equally likely. It's a 1 out of 3 chance for each one because whatever he does on the first call doesn't affect the next one. So this would be considered an independent event. So you could really write that as 1/3 to the 5th. Some people would write it that way. It might be a little bit easier to deal with. That means it would be 1 out of 243. So it's an independent. One sale does not affect what the next one would be. All right, so we're going to come back to this example in just a second. We're going to talk about complements and then talk about another way to look at this. So the complement of an event is if you look at the total number of ways something can happen, and then the number of ways that something can't happen, and you put them together, that gives you the total number of outcomes. So the probability of an event occurring is always 1 minus its complement. So when we talk about, say, there's 60 ways one thing can happen, 40 ways it can't happen, those together would always equal 100% of the time. So it's kind of a nice way to calculate things when it might be more complicated to figure out the other part. So let me show you what I mean. So let's go back to the sales call idea. So it's still 1 out of 3 times, so 1 out of 3 chance of making a sale. What is the probability of making a sale on at least one of the contacts? So the probability of a sale on at least one. All right, so he's making 5 calls, right? 5 potential clients. So if he makes a sale on at least one of the calls, that means he could make 1 sale and 4 no sales. So we'll kind of keep track here. 1 sale, 4 no. Or he could make 2 sales and 3 no. He could make 3 sales, 4 no's. Or he could make 4 sales. Am I not adding to 5 here? Oh, sorry, 2 no's, going the wrong way. 4 sales and 1 no, or he could make all 5 sales. So the only option that's not being represented here is no sales at all, and so 5 no's. So no sales, everything's a no. So instead of trying to go through and calculate all of these, it would be a lot easier just to do 1 minus the probability that they have no sale. So I think when you think about what that would look like, it might be faster to calculate that. So we can think about the complement instead. So the probability of at least 1 sale is going to be the same as 1 minus the probability of no sales, because that's the only one not represented. Everything else is there. Well, what's the probability that they don't make a sale? Well, they make a sale on 1/3 of the calls. So that means they're not going to make a sale on 2/3 of the calls. And then again, how many calls are we making? 5 of them, right? So we'd have no sale 5 times would be 2/3 to the 5th. It's a way easier way to calculate that instead of adding up all of these, right? We'd have to calculate the probability of all of those and add them together. That's way faster to do it this way. So 1 minus my 32 over 243, and you end up with 211 out of 243. It's way more likely that he's actually going to make at least 1 sale, right? So 1 sale, 2, 3, 4, or all 5. is going to be a pretty likely outcome. So again, these are independent events though, right? What I do on one call doesn't affect what I do on the next. So that's the part 2. So we talked about independent versus dependent, and then mutually inclusive versus exclusive. Is there overlap? Is there not overlap? Be careful on those to subtract them off. And then does my event that I'm talking about, does it affect what happens next or doesn't it?